This is the reality of Malaysia's monsoon season, where extreme flooding can drown an entire harvest in a matter of days. But just a few months later, that same land faces a different threat. Severe mid-year dry spells leave the earth parched and cracked. Crops must endure a cycle of too much water, followed quickly by too little. Traditionally, determining if a specific crop could survive these extremes meant planting it and waiting. You might spend 10 years tracking weather patterns and losing harvests just to learn that a specific site isn't viable for that crop. MsiaGen Education AI provides a different path. By using a stochastic weather generator, the platform creates statistically realistic synthetic climate data. This allows you to test how a crop will perform under local weather conditions without waiting years for results. This platform operates as a reactive computational workspace. It isn't a static lecture. You are actively analyzing variables to solve specific agronomic problems. You work through a precise 8-step process. This maps out a clear progression, testing your crop's viability against the historical weather patterns of any chosen site in Malaysia. By grounding every decision in statistically validated data, you replace guesswork with interactive analysis. The process begins by setting up your site inputs. Across the first 6 steps, you build a climatic profile by analyzing the distribution of temperatures, wind speed variability, and persistent rainfall patterns. Throughout each section, you follow a specific behavioral loop. First, you observe the data on screen. Then, you explain the agronomic impact of those observations. Finally, you predict the outcome of changing a specific variable. This loop forces you to mentally map the consequence of a change before you manipulate the system, which helps build analytical intuition. Everything converges in Step 7. This is where the raw weather data meets the biological needs of a living plant. You configure 4 crop parameters alongside 2 soil parameters, sand and clay content. This highlights a critical trade-off in soil physics. If your soil has too much sand, water drains too rapidly. If it has too much clay, the soil holds onto the water so tightly that plant roots cannot access it. You have to find the balance, the available water capacity, that prevents crop stress. Consider a crop like oil palm. Because it is deep-rooted and relatively drought-tolerant, it changes the risk profile, surviving dry spells that would damage a more shallow-rooted plant. Watch the soil water storage heat map. As we increase the root depth parameter, the site's risk profile changes. The dark red zones, indicating low water availability, shift to blue as the plant gains access to deeper soil moisture. This shift in the soil's capacity directly updates the crop stress table. Proper parameter alignment lowers the cumulative water stress days, providing a quantitative reading on whether the crop can actually thrive at this site. Let's apply this. What happens if you plant a shallow-rooted crop in soil that is 80% sand during a severe May to July dry spell? You would likely see agronomic failure. Because the sand cannot retain moisture during peak heat, the water storage drops to 0, triggering immediate warnings on the crop stress table. Evaluating risk requires balancing the water demand of your plant against the physical water-holding capacity determined by the soil's sand-to-clay ratio. Once you have made your observations, the integrated AI tutor evaluates your responses. Powered by Claude, it analyzes your typed reasoning based on the specific climate data you just worked with, rather than using a generic answer key. If an answer is incomplete, you will see a screen like this. The AI provides a partial score and identifies what is missing, such as an error in your logic regarding soil texture, allowing you to revise and resubmit. It also processes answers in Bahasa Malaysia. This feedback loop turns the AI into a partner in the learning process. It handles initial assessments, which allows the instructor to focus on addressing the broader patterns of understanding across the whole class. The analysis concludes in Step 8. This is where your chosen crop and soil parameters finally align with the specific climate profile of your site. Look at this completed crop stress table. When the parameters match the environment, you generate green, safe metrics across the entire multi-year record. By this point, you have stress-tested the environment and evaluated the crop's viability without planting a single physical seed. Building a reliable analytical framework for agricultural planning depends on this methodology. You maintain the cycle of observation and prediction while balancing climate data and soil texture against the plant's rooting depth. The combination of the 8-step analytical process and personalized AI feedback is designed to build a more grounded understanding of how tropical climates impact agriculture,